introduction, we'll go right into groundwater treatment. So what are some of the typical challenges, typical issues in groundwater treatment? So iron removal obviously is one of them, manganese as well, and these are not typically considered health concerns, but they do have a secondary maximum contaminant limit that tries to establish sort of a good level for you to treat towards to make your water aesthetically pleasing. Once you start getting iron and manganese above these levels, you run into things like staining of fixtures. The water has an unpleasant appearance. It can look reddish. And so a lot of communities will really try hard to get these numbers down and make the water very aesthetically pleasing and reduce customer complaints, as well as encourage people to actually drink the tap water and maybe buy a little less bottled water. Hydrogen sulfide reduction and for odor control is a big challenge. There's a lot of parts of the United States where this is a major issue. And this is actually one of the specific areas where mixed oxidants has a very unique chemistry profile that can ease and make it a lot easier to do hydrogen sulfide removal. And finally, ammonia removal. And we'll talk about each of these briefly. So one of the things to keep in mind as we're looking at groundwater treatment is mixed oxidants, as I mentioned earlier, has a little bit different chemistry. It tends to speed or extend oxidation reactions. So in the case of iron and manganese removal, it can be used to oxidize iron and manganese. And for those of you who are familiar with manganese removal, you may say, well, wait a minute, chlorine is a really slow reactor with manganese, and usually potassium permanganate is used, and that's absolutely true. I would say probably most commonly you would see potassium permanganate used to get rid of the manganese in particular. But mixed oxidants has been proven repeatedly to speed that reaction along, and when combined with a green sand filter, will allow you to use chlorine as a precursor as opposed to potassium permanganate. Hydrogen sulfide removal is a very similar thing. Normally, when you use just chlorine to try to take care of hydrogen sulfide, the reaction pretty much likes to stop at elemental sulfur, which means you have to have a lot of equipment. Mixed oxidants is demonstrated in several installations to drive that reaction all the way through to its soluble form. So looking at these just a little bit more closely, here's a typical process flow diagram, and obviously this doesn't cover every contingency that you're going to see out there, but this is a typical process flow diagram for iron oxidation and removal. And one thing I should mention is that I get a lot of questions that says, will mixed oxidants, quote, eliminate iron, or will it eliminate manganese? And it's important to realize that when you oxidize iron and manganese, it doesn't, let's say, dissolve them or destroy them from the water source. It converts them into it oxidizes them and converts them into a soluble form. So in this case, mixed oxidants and for that matter, hypochlorite are part of the solution to the problem. So it can be used as a very economical source to oxidize the iron prior to the filters. And you can see we show a little MIOX system there with the day tank and a pre-feed going just prior to your media filters, which could be pressure or gravity. That tends to be chosen based on the size of the plant and the economics. So the water would come out of the well, be fed to the filters, and prior to the filters, you would dose some of the hypochlorite or mixed oxidants to oxidize the iron. The iron would then be filtered out via the media in the filters and periodically washed back out and sent to waste. And then we show a second disinfection point for residual out to the storage tanks or the distribution system. So it's a relatively simple operation, relatively simple product, or I should say a process train, but nonetheless, very economical way of doing it. Manganese process looks very similar. So once again, the water comes out of the well pump. Dose, in this case, we recommend mixed oxidants to help oxidize the manganese faster than the hypochlorite. In addition, you're going to want to make sure that the media in your filters is a green sand type media, whether this is traditional green sand or green sand plus, or a number of the coated medias that are out there that some of the suppliers provide that have a manganese oxide coating on the media itself. And this helps to further catalyze that manganese reaction and take out that manganese through the filters. And then once again, you can do post-dosing for residual out to the storage tanks. Some communities will actually go ahead and overdose the mixed oxidant or the hypochlorite prior to the filters and carry that distribution, or I should say that chlorine residual through out to the distribution system as well and eliminate that second dosing point. It all depends on what your preference is. If you like to have a high degree of control over your pre-treatment process and a high degree of control over your residual, then you can separate that out into 2 pumps. So now we'll go ahead and move on to hydrogen sulfide. And once again, I want to remind you, we're going to be going into more of the detailed chemistry on these and how this works in our further sessions. You can see that it's just very high level on both of those. Fortunately, iron and manganese are pretty easy ones to deal with. Now we're going to go ahead and move on to hydrogen sulfide. Hydrogen sulfide, as many of you are likely aware, is it usually identifies itself in a groundwater source or in a drinking water source as a rotten egg smell. It can also sort of evidence itself as a burnt match smell, depending on exactly what the treatment and things like that look like at the plant. So there's a lot of different options that people have. One thing that's fascinating with hydrogen sulfide, and I don't have the graph in here, I'll show you a graph in the next presentation, but hydrogen sulfide can exist either in a soluble form or a gaseous form in your water stream, depending on pH. So at a lower pH, it can be present almost entirely as a gas, and gas is the odorous form of it. At a high pH, it can be 95% or better in the soluble form, and that's actually more challenging to remove. So, and most of the time at groundwater facilities, you're already in that pH range that most of it is going to be in your soluble form. And it doesn't take very much of that. You can have a small amount of hydrogen sulfide and 5% of it is still in gaseous form and you can still smell it. But that is still in the range where you're going to be the most challenging to get rid of it. So you have several different options. Option 1 is to lower the pH or acidify the stream. Run it through a degasifier basically you're lowering the pH to turn everything into gaseous form, go through a degasifier, and then raise the pH back up. And as you can imagine, this can be a rather expensive proposition to do. It's not terribly popular. If I had to estimate, I'd say, based on my experience, probably less than 5% of the hydrogen sulfide removal systems out there go this route. It also means that you have to bring acid and you have to bring caustic onto the site to accomplish this, which is not terribly popular with a lot of operators. So option 1 is not particularly popular. Option 2 is you can use ozone to drive the reaction all the way to sulfuric acid, and that actually then is a soluble, non-odorous form of the hydrogen sulfide. But once again, as you can imagine, ozone can be kind of pricey and not a particularly popular choice just to handle something like hydrogen sulfide. I'd say one of the most common options is option number 3 here, which is degasification, which is typically optional. You add bleach or hypochlorite to it, wait about 1 to 2 hours, and then filter the elemental sulfur that is formed. So it'll actually form sort of what looks like a white yellowish sort of particulate, ultrafine particulate in the water, which then subsequently needs to be filtered out. Option 4 is to dose mixed oxidants. Mixed oxidants have been demonstrated to actually behave very much like ozone in this case, in that it drives a reaction to sulfuric acid, eliminating the need for some of that additional equipment. So let's take a look at a couple process trains here to show you that comparison. So traditional hydrogen sulfide removal can be onerous and require significant capital upgrades. So if you're a community that currently is just pulling water out of a well and putting it into the distribution system and dealing with the hydrogen sulfide odors and you're looking to make a change, this would be a very common flow scheme that you might be considering. So you would come out of the well pump, you might go through a degasifier, or air stripper, or some people even call it an aerator. And really what this is for is, even though the majority of it is not in, let's say, the gaseous form, at least you get some removal for in essence, free. So for the cost of driving a little squirrel cage blower, you can remove at least a portion of the hydrogen sulfide out of the water stream. Typically then hypochlorite is dosed at the outfall of that degasifier and then go to a detention tank that can typically be sized for about 1 to 2 hours of detention time. portion of that will form elemental sulfur, which then it has to be filtered out with either pressure or gravity filters. And then from there you go into the storage distribution tank. So what does a mixed oxidant version look like? It's much simpler. So you come out of the well pump, you dose mixed oxidants in for hydrogen sulfide and chlorine residual control. And since it drives that reaction all the way through, the way you can look at it is it drives it to sulfur but continues to oxidize the sulfur into basically sulfuric acid, which then is soluble and it can be sent out to the system. So very cost effective if you're looking at a retrofit to try to address this as a problem in your plant. This is obviously quite a bit more cost effective. You reduce a lot of potential capital equipment. But in addition to that, you can also reduce the potential for double pumping. So for example, in this previous example, you would come out of the well pump, and in many cases you would break head, and then you'd go through your system and you need to repump out to the distribution system. In this case, you can avoid that repumping with the use of mixed oxidants for hydrogen sulfide removal. So now moving on to ammonia. Ammonia removal can be accomplished in a few ways. There are some systems out there that will actually use biologically active filters in the drinking water plant to metabolize the ammonia and get rid of it. This can be quite effective, but in some cases can actually require the addition of a food source such as methanol or something like that in order to accomplish it. If there's not enough ammonia in the water to keep the bugs fed, you may actually need to supplement it with some other food source in order to keep the bugs fed. In addition, this can sometimes be a little bit of a public relations challenge. It's kind of counterintuitive to your constituents that you're using biology or bacteria, let's say, to treat water in a drinking water treatment plant. So some people don't even like to go down this path too far because they're just worried about, if the word gets out, what is the public perception going to be like? So even though they're beneficial bacteria, a lot of times people don't like to have to try to handle that bacteria in a drinking water plant. You can also use nanofiltration reverse osmosis. Operating costs can be quite high with those alternatives, and then in addition to that, you have to worry about disposing of a concentrate stream, which can be a challenge. Some communities just don't have a way of getting rid of that high TDS wastewater, and it can be a significant portion of your flow stream. Most nanofiltration RO systems will get between 75 to 90% recovery, meaning that you have approximately 10 to 25% as a waste stream that you need to get rid of. And that in and of itself can sometimes limit the ability to adopt this technology. Finally, you could do break point chlorination to convert it to nitrogen gas, which is probably one of the more common ways in a drinking water system to actually accomplish this. Can require a high volume of chlorine. Can be a little bit of a challenge to control as well. If you look at the dose curve, you will actually see that you need to dose past a high point, and then it sort of drops off to a low point as you begin to oxidize that and you break through that chlorine dosing curve, or the ammonia dosing curve. So if you're on the one end of the curve, it can be a challenge to control. You need to make sure you get up and over, quote, the hump, as they call it. And again, in the future ones, we'll go through this in more detail and show you some of these curves in more detail. Mixed oxidants offers superior ammonia removal because it actually tends to require quite a bit less. A lot of systems in my previous life that we would design, we would assume about a 15 part per million free available chlorine dose to make sure that that break point occurred. If you look at the actual equations, one of the ways that you can run through a mass or a chemistry balance on ammonia is it would tend to imply that you might be able to actually do it with quite a bit less, more or closer to a stoichiometric ratio of approximately 7 milligrams per liter. Mixed oxidants tends to, or I should say, has been demonstrated a number of times to dose much more closely to the stoichiometric ratio. So we normally recommend that you would dose this between 8 to 10 parts per million, which is obviously quite a bit less than the design that you'd be looking at for regular bleach. So that reduces chemical consumption in some cases by almost 50%, and obviously reduces chemical costs by as much as 50%. We show a little bit of a chart there that shows an ROI for a typical installation when comparing bulk hypochlorite to mixed oxidants, and in that case, the return on investment can be less than 2 years. So as we kind of wrap up this section, I like to post this up. It's just kind of a handy little cheat sheet. We get this question a lot. How do you actually show the, or how do you size systems to address these various issues in groundwater? So this is what we call a little bit of a cheat sheet for you. And the further left-hand column, for this left-hand column, you can see we have the various constituents: iron, manganese, hydrogen sulfide, and various forms of ammonia. The stoichiometric ratio, so if you were going to dose precisely the amount according to the chemical balance, what would that actually be required as free available chlorine, and then what we typically use for sizing purposes. So we like to be just a little bit conservative to make sure that you're covered on your system sizing, and also to kind of take into account some unknown constituents in the water that might present a chlorine demand or an oxidant demand. And so we'll typically use the values in the for this right-hand column in order to size the system. And you can certainly feel free to use these if they help you out. So we'll move on to surface water treatment. So some typical issues in surface water treatment: ammonia removal. I won't go over that again, but ammonia is present in a number of surface water supplies in some cases. I've tended to see over the years more in groundwater because ammonia in surface water can be metabolized, but occasionally we have customers on surface waters that will see ammonia removal or ammonia as a problem, in which case you would go back to the discussion in the previous section. Probably the most common thing that we run into as far as a challenge in surface water treatment is disinfection byproduct formation from both THMs or trihalomethanes and haloacetic acids or HAA5s. And then another challenge in surface water treatment is how do you optimize your operating expense? So are there opportunities, let's say, to reduce coagulant usage? Are there opportunities to improve enhanced coagulation in the surface water treatment plant? And the disinfection byproduct discussion and some of these reductions in operating expense will go a little bit hand in hand. And so we'll just go ahead and move on to that. So when we look at disinfection byproduct formation, we really try to explore with our customers, where is the challenge actually coming up? So in a sense, disinfection byproduct troubleshooting can help you identify a way forward when looking at how to help solve this problem. So if we look at just this very simple surface water treatment train, so come in from the surface water source, go through flash mix, flocculation, clarification, and this can look a bunch of different ways. This could be a traditional flock set basin, solids contact reactor clarifier, a cone style clarifier. There's a lot of different pieces that you can see for something like ballasted flock reactor, for example, might be something else that you would see there. Go through filtration. Many cases, this would be gravity on a surface water source. Finally to the clear well, and then out to the distribution system. So when we start looking at it, we try to figure out where is the disinfection byproduct challenge actually coming into the plant, or where is it actually identified. And a really good break point to sort of get a handle on how to handle it is right before the distribution system. So if your disinfection byproducts are high, measured prior to the distribution system, improved pre-treatment is obviously something you need to look at. So if you're already exceeding your disinfection byproduct goals prior to the distribution system, optimizing your pre-treatment is going to be critical to your success. If your high disinfection byproducts are forming in the distribution system, you can consider mixed oxidants in the distribution system. Just simply replacing your current disinfection dosing regime with mixed oxidants can actually help in this case. So we'll look at a couple of those more specifically. So again, if we're looking at this treatment train, where potentially would mixed oxidants or MIOX fit in? You might actually do some pre-oxidation prior to the clarifier to induce a microflocculation effect, and this will depend on water quality, but this can enhance the pre-treatment portion of it. Or if you're seeing that you're getting disinfection byproduct formation in the distribution system, you may just go ahead and substitute for your final disinfection and assist with that. So what is the microflocculation effect? So the microflocculation effect can occur in some surface waters, and it's actually surprising the number of surface waters that this does occur in. And it's a fairly well documented process, and in fact, there are some water quality parameters such as TDS, turbidity, alkalinity that you can use to help predict whether or not this effect will occur. And in fact, our website does have a microflocculation effect calculator. So you can go on there and put in your typical water quality, and it'll give you an indication of, does this look like a good candidate? Is it a borderline candidate? Or is it a good candidate for the microflocculation effect? And what the microflocculation effect is, in essence, is by adding a small amount of mixed oxidant prior to the coagulation, so you add the mixed oxidant, followed up with your coagulants, polymers, whatever it might be, you can actually see that the settleability and the removability, if that's a word, of the floc is greatly improved. And this then can enhance carbon removal and disinfection precursor removal significantly. And along with that, it can also, in many cases, greatly reduce the amount of coagulant required to at least get the same or even better effect. So a great example is you might see with a 20 or 30% reduction in alum usage, by adding, let's say, 0.1 part per million of mixed oxidant, you can achieve a 20 to 40% reduction in your coagulant usage and still see a higher settled water turbidity and a higher organic carbon removal through the clarification process, and then carries on through the filters. And by reducing that carbon and improving your flocculation process, your enhanced coagulation process, you reduce the amount of carbon precursor, or I should say disinfection byproduct precursor, and thus have a lower formation potential in your distribution system. The really nice thing about this process is once you've sort of identified yourself as a candidate, it's very easy to jar test this. And so you can set up your gangster. We run a control group of what are you currently doing with both some coagulant dosages above and below what you're currently doing, and then do the same thing again with dosing a small amount of mixed oxidants, and it points you in the direction of whether or not this effect will take place. And you can do some further studies to see, how much does it improve the quality of the settled water. So we've done a number of pilots, have several installations out there that are doing this exact same thing and have demonstrated up to 40% alum reduction. This is just one such example at off of the water that comes off the Rio Grande. And the plant capacity in this case is 8.2 million gallons per day. And the bar graph there that you can see is showing a comparison of settled water turbidity at various coagulant dosing ranges of 35 to 60 parts per million, and the blue line is with no MIOX pre-feed, and the line down the red line is with MOS pre-feed or mixed oxidant pre-feed. And you can see that in each of these cases, which is a small amount of pre-feed, you actually get better settled water turbidity, and hence you're likely also getting a reduction in additional precursors and other contaminants in the water as well. So in another interesting example about this is, even apart from the reduction in disinfection byproduct formation, if you can reduce that pre-oxidate or that polymer and or coagulant pre-feed dose significantly, you can see a very, very quick payback on a large plant. So in this case on 7.5 mgd, the payback with the chemical savings on the coagulants, and this was in this particular case study, it was 30% reduction in alum and polymer. They saw approximately a year and a quarter payback by swapping out the mixed oxidant. Now, conversely, if DBVs are forming in the distribution system, this may indicate the presence of a biofilm in your distribution system. So a common symptom of this would be, I'm looking at my pretreatment process, I don't have significant disinfection byproducts coming out of the back end of my filter, or even just going out of the clear well prior to the distribution system. But I'm seeing that I have to put in a lot of chlorine, let's say 1.5, 2 parts of chlorine to maintain residual in my distribution system, and at the same time I'm seeing disinfection byproducts increase in my distribution system. If you're seeing something like that, it indicates that there is a consumer of chlorine in the distribution system, which can oftentimes be attributed to a presence of a biofilm. That biofilm, in addition, creates additional carbon source, which can then finally create more disinfection byproducts. And like I said, the most common symptom of this is a large chlorine consumption in the distribution system. So the use of mixed oxidants can reduce or eliminate the biofilm, which then reduces your DBP formation and reduces your chlorine demand in the system as well. So here's a couple of interesting pictorial representations of what we're talking about. So on the left-hand side, and this is not a drinking water system, but it's a hard application. This was a spa in Japan that was running into biofilm issues that led to Legionella outbreaks, and in fact, a couple people were actually killed as a result of the presence of Legionella. So they approached us. They looked for are there any chemistries out there that can help eliminate this biofilm. They found us by doing a search and installed one of our systems. And you can see the bore scope of the recirculation piping on the left. And after 22 days, another bore scope was performed on the right. And you can see that by simply switching between their regular bulk hypochlorite to mixed oxidants, they were able to, in essence, completely clean that recirculation loop out. In addition, they were seeing that they were having to dose approximately 1.5 milligrams per liter of sodium hypochlorite to just barely maintain a residual of 0.2 milligrams per liter. Once that system was online for 22 days, they were actually able to reduce their input dosage significantly to approximately 0.6 milligrams per liter, and their residual came up to about 0.4 milligrams per liter. Moving over to the right-hand side, you see a case study for one of our installations in Texas that was using gas chlorine, and they noticed that there was a brown sort of slimy film in some of their distribution system piping at a location of only 200 foot away from the plant. So this is where they had to get into the pipe to do some repairs. This was a visual observation that was made before the mixed oxidant system was put online. After 1 year, there was some maintenance being done approximately a half mile away from the plant, and you can see that this pipe, this white pipe here, shows no evidence of biofilm whatsoever. So it's just yet another one. We have a number of these installations that we can talk to you about that this same effect has been observed. So you can see in that case, if you've eliminated that biofilm, you've eliminated a significant consumer of chlorine, as well as the potential for additional carbon source for disinfection byproduct. So the proof is in the pudding. What does that mean for people, for folks? And we got a lot of case studies that talk about the disinfection byproduct removal, or I should say reduction. This is just one such case study for one of our installations in Puerto Rico. And these bar graphs show a year-on-year quarterly comparison between Q2, Q3, Q4, and then back to Q1. And you can see that the red lines here are the chlorine gas during that same time frame, and then 1 year later, what did the disinfection byproducts or the trihalomethanes look like with the introduction of mixed oxidant? And you can see that in every case, it's significantly lower. And even Q4, it's actually lower than by more than 50%. So other applications and final disinfection, this actually, one thing that was really fun about putting this presentation together, and I will admit it got a little bit longer than we originally thought it was going to be, because we got a lot of great feedback from folks that were interested in participating in it. One of the comments that we saw a number of times was, are you going to talk about membrane cleaning to improve CIP interval and or membrane life? We weren't originally planning on doing that, so I have put in just one slide to talk about this briefly. And if there's one thing I'd like to ask the folks on this call, if you find this useful and you participate in some of the other ones, please let us know if that should be a completely separate webinar, which we would be happy to put on, or if we should try to stuff it into, let's say, the surface water treatment one. But if you've got an opinion, please let us know. We love the feedback. And then, of course, final disinfection, which I haven't talked on, but is really the tried and true traditional application for drinking water. So a mixed oxidant solution, and this is the only slide I'm going to talk about, but this goes right back to the discussion that we've been having about the superior biofilm removal, superior organic control. One of the big challenges that folks run into with ultrafiltration membrane systems out there is actually controlling that biofouling over the long haul of the plant. And I used to work for a company that sold one of the top brands of microfiltration, ultrafiltration systems out there for drinking water, and I can tell you from firsthand experience that can be a very big challenge. Controlling algae into the system, controlling biological growth over time can lead to shorter membrane life and shorter CIP intervals. So we have a few systems that are out there that have been either dosing a very low dose of mixed oxidants prior to the system continuously, or are running CIP, and in those cases we've seen that those systems get very long, much longer membrane life than those that do not. We don't have 100 installations out there, but we'd love to have more. So we could talk about this. We'll talk about this in more detail in the surface water, or as a separate carve out, where we can go through some of the numbers and some of the ways that you would actually do this. But the mixed oxidant chemistry is quite compatible with the membranes. Most of the manufacturers have looked at the compatibility not with only the membrane material, but with the potting and the O-rings and the housings and things like that, and have found that it is quite compatible with the membranes and doesn't cause any oxidation degradation. So that's one thing to keep in mind. Second, it can be used as a pre-dose and can also be used for the CIP makeup. One side benefit of it is the solution that comes out of our generator is also warm, and so it can actually even reduce your heating requirements on your cleaning regime for your organic cleaning. So definitely something to think about and something to look at, and we'll talk about that in more detail in the future. Finally, a replacement for final disinfection. And if this is the only thing you're trying to do, let's say you've got no disinfection byproduct problems, you've got no problems with pretreatment, you just are looking for a cost-effective alternative for disinfection, this can still be a very cost-effective replacement for bulk bleach delivery. And this is a graph that shows kind of a comparison of our return on investments at various costs per gallon of hypochlorite. The bottom line is at approximately 95 cents a gallon, which is pretty cheap these days. The red is $1.25 a gallon, and $1.75 a gallon is on the top. And we've actually seen numbers even higher than that in some cases as well in certain rural parts of the country or rural parts of the world. And in this case, the graph shows, again, on the x-axis, the number of years from 0 to 18, and the cumulative savings. And so in this case, where the line crosses the 0 is what your payback is. So at $1.75, you're looking at 2 years, but even at $1 or closer to $1, 95 cents a gallon, it's right at about 5 years payback. And this will vary a little bit depending on what your salt and energy cost is, but this is a fairly typical payback curve. So just for simple replacement of disinfection, this can still be very cost effective. Then if you go ahead and you pile on all the other things we talked about earlier, such as hydrogen sulfide removal, disinfection byproduct reduction enhancement, this payback curve can get very, very attractive.